Everyone calls it the cheese grater. Almost no one understands why it actually works. Each opening in the Mac Pro's aluminum skin isn't a hole. It's a pair of hemispherical cavities, bored from opposite faces, forming scalloped internal channels that no simple perforation could replicate. The real secret isn't the pattern you recognize. It's the fluid dynamics hidden inside the metal. This industrial design language spans both the front and rear faces of the workstation's aluminum enclosure, establishing a unified aesthetic that is entirely functional. While casual observers immediately designated the pattern as a cheese grater, the nickname only identifies the outer surface. It does not explain the physical mechanism at play. These openings are not standard perforations. In typical hardware design, ventilation grills are stamped or punched out of sheet metal, producing flat, two-dimensional holes with sharp, restrictive edges that generate resistance. Here, the exterior functions as an engineered outer panel rather than cosmetic branding. Both the front and rear faces of the aluminum chassis are subjected to the exact same treatment, rendering each individual opening a three-dimensional cavity carved directly into the metal. Instead of using high-speed presses to punch holes, the production process relies on precision, computer-controlled machining to sculpt the material from solid metal. By carving away material from both sides of the solid aluminum panel, the design team created a physical structure that Apple framed as containing more air than metal. It is a continuous, highly calculated geometry that treats the computer's outer skin not as a passive cover, but as an active, structural component of the machine's overall physical architecture, designed to withstand the physical demands of a professional environment. Each of these three-dimensional apertures is formed by a pair of hemispherical cuts bored into opposite faces of the aluminum panel. Instead of a uniform cylinder passing straight through the metal, the overlapping entry paths create a three-dimensional passageway. Where the two offset spheres meet in the center of the plate, they form a scalloped, interlocking channel. This geometry fundamentally alters how the panel interacts with moving air and mechanical forces. By carving out rounded cavities rather than drilling straight holes, the design increases the total internal surface area of the metal skin. When air flows through this network, the curved walls provide a gradual, continuous transition. Unlike the flat, sharp edges of a traditional stamped vent, which force incoming air to shear abruptly and create high-resistance eddies, these rounded pathways guide the streamlines smoothly. This reduction in shearing minimizes local turbulence, which in turn lowers the broadband wind noise generated as air enters and exits the chassis. Beyond fluid dynamics, this intersecting geometry provides a distinct mechanical advantage. A flat sheet of metal with a large portion of its material removed by standard drilling loses much of its structural integrity, leaving it prone to twisting and bending. However, because the spherical cuts leave a continuous, undulating web of aluminum behind, the physical load is distributed evenly across the curved arches of the remaining metal. The panel retains the torsional stiffness of a much heavier solid sheet, allowing it to serve as a rigid, load-bearing outer frame while remaining highly porous. Converting this theoretical geometry into physical reality requires abandoning standard high-volume manufacturing methods. In mass production, ventilation grills are typically stamped out of thin sheet metal in a fraction of a second, using high-speed presses to punch holes through the surface. The Mac Pro panel rejects this approach. Instead, each front and rear face starts as a solid, monolithic block of extruded aluminum. To create the interlocking lattice, Apple routes these billets through computer-controlled machining centers. 5-axis CNC mills carve away material from both sides of the plate, using highly coordinated tool paths to scoop out the hemispherical cavities. This is a subtractive process where the design is realized not by bending or stamping metal, but by systematically carving it away, turning a vast majority of the raw alloy block into piles of aluminum chips. This subtractive route is inherently slow, demanding substantial machine time for every single unit. Because the cutting tools must physically traverse the metal to sculpt each intersecting curve, the rate of production is strictly bound by the physics of CNC milling. The finished panel serves as a literal record of this intensive manufacturing choice, with faint tool marks tracing the path of the cutter. This extreme level of machining establishes a hard physical limit on how complex an enclosure can be when scale, cost, and raw material are balanced against performance. The lattice panel acts as the intake boundary for a larger, active thermal system. Behind this front face sit 3 large axial impeller fans stacked vertically to cover the entire height of the internal chamber. These fans do not simply circulate air inside a closed box. They drive a single, unidirectional cooling path that runs straight through the workstation from front to back. As air passes through the intake, it moves in a straight line across the main motherboard, the processor, and the expansion modules before exiting through a rear blower. The interior of the workstation uses an open-frame architecture. By removing the physical barriers, drive bays, and internal plastic shrouds common in traditional towers, the design minimizes resistance along this path. This allows a massive volume of air to pass through the chassis with minimal static pressure buildup. To control the acoustic profile of this high-volume movement, the front fans employ a specific geometric arrangement. Instead of equally spaced blades that produce a concentrated acoustic spike, the impellers feature randomized blade spacing. This variation disperses the blade pass frequency across a wider frequency band, flattening the noise curve and shifting the sound from a distinct whine to a gentle, broadband hum. This coordination of the structural enclosure, the open chassis, and the fan modules functions as a single thermal strategy. Because the air path is highly direct, the fans can spin at lower rotational speeds while maintaining the required flow. Under sustained processing workloads, the workstation dissipates heat effectively while remaining barely audible in professional workspaces. This emphasis on silent, high-volume airflow represents a complete departure from Apple's previous desktop architecture. In 2013, the company had attempted a radically different cooling concept, a compact, glossy cylinder built around a single central heat pipe structure known as the Unified Thermal Core. While elegant, that design forced the CPU and dual GPU units to share a single triangular heatsink, cooled by one top-mounted fan. Under sustained professional workloads, this shared thermal path quickly ran out of headroom, throttling performance and limiting modular upgrades. When John Ternus assumed leadership of Apple's hardware engineering, his team used the cylinder's thermal bottleneck to redefine their entire design philosophy. For the 2019 redesign, Ternus bypassed the company's historical obsession with thinness. Instead, engineering priorities shifted entirely toward raw cooling capacity and acoustic performance, framing the new tower as a deliberate, professional-first workspace machine. The machined aluminum shell serves as the primary load-bearing skin of the workstation, eliminating the need for an internal support cage. This structural design allows the heavy chassis to be lifted directly by the lattice, which forms a secure, ergonomic grip across its entire surface. Because the manufacturing process remains visible through the subtle cutter marks left on the metal, the physical reality of how the machine is made becomes its central aesthetic. Rather than hiding the raw demands of fabrication and thermal management, the design exposes them. Here, near-silent operation is a standard engineering requirement for sustained professional work rather than a luxury feature. The enclosure rejects superficial styling, establishing a design philosophy where the physical integrity of the object is defined entirely by its structural and thermal performance. As compute demands escalate, Performance is no longer limited by silicon, but by thermodynamics. This lattice proves that sustaining power requires treating the enclosure not as a shell, but as an active component. The future of hardware design belongs to those who can shape physics. Share your thoughts below.